Hey guys, today we're doing Chapter 2, Section 4, which is on exponential functions. So an exponential function is a function of the form f of x equals ab to the x, such that a is non-zero, b is greater than 0, and b is not equal to 1. So why is that important? Well, a can't be 0 because if a was 0, then you'd just be multiplying some number by 0 every time. And when you multiply by 0, you get 0, so that would just be a constant function. Same thing if b equaled 1. 1 to any power is just 1. So you would just be taking your a times 1 if b was 1, which again would just be a constant function. So neither of those would be considered exponential. All right. If b is greater than 1 and a is greater than 0, then you have what's called an exponential growth function. So basically, if we assume that this is my x-axis and this is my y-axis, your exponential growth is going to look something like this. Okay, so notice that as your x values are getting bigger, your y values are getting bigger. That's why it's called a growth. Okay, and also notice that this is an asymptote, so the y-axis is going to be an s-asymptote, and asymptote as my x values get smaller, they're going to approach 0. Okay, if you have an exponential decay, a decay is pretty much the same thing, it's just facing the other way. So if this is my x-axis, this is my y-axis, my decay is going to look something like this. So as my x values are getting larger, my y values are approaching 0, and as my x values are getting smaller, my y values are getting larger. So same type of thing, it's just they're basically mirror images of each other. So let's do some examples. In 1994, the population of the Las Vegas metropolitan area was about 1,076,000, with an average annual growth rate of 6.5%. Assume this growth rate continues into the future. Let's estimate the population of Las Vegas in 1995, 1996, and 1997. Well, if my original population was in 1994, okay, so that's this was in 1994, and I know that it's growing by 6.5% per year, that means that after a year, so for 1995, I would just be taking my original and I would be multiplying it by 1.065 because it's growing at a 6.5% rate, so that means that I have to have 1.065. Okay? And if I multiply those together, I get 1,145,900. Oh, 940. Okay, so that would be my population in 1995. Well, if I want to find my population in 1996, again, I'm growing by 6.5%, so I can just do the same thing, except I can take this times 1.065. And when I do that, I get 1,220,426. And then again, if I want to find my 1997 population, I can just take that previous term and I can multiply it by 1.065. And when I do that, I get 1,299,753. Okay. So that's probably not the most efficient way to do this. So let's think about how we could possibly make a function for this. So let's express the population p as a function of n. So I've got p of n, where n is my independent variable. And I want to find the number, the population, the number of years after 1994. So what I'm going to do is I'm going to start with my a value. Remember that my function should be in the form ab to the x because it's exponential. My a value stands for my initial value. So my initial value was 1,076,000. And then my b value stands for my growth rate. So that's how much I'm actually growing by, and that was 1.065. And then instead of writing an x here, I'm going to write an n because n is the number of years after 1994. So this function is going to model my population growth. Now I can estimate the population of Las Vegas in the year 2020. because I can just plug a number into this function here. So remember that this is the number of years after 1994. So I need to figure out what my n value is. So if I take 2020 minus 1994, you should get that your n value is 26. So I'm going to take 1,076,000 times 1.065 to the 26th power. I'm going to plug that into my calculator. And when I do that, I get 5532253. So 5,532,253. Alright, a particular prescription drug has an initial concentration in the blood of 50 milligrams per milliliter and is absorbed by the body so that each day its concentration drops by 68%. What is the drug's concentration in the blood after the given amount of time? Okay, remember that in here it says its concentration drops by 68%. Well, my formula is calculating how much is actually left. So if I'm dropping by 68%, that means that I have 32% left. So that's going to come into play here. You want to make sure that we're doing that the right way. So if I start with 50, and after one day I'm dropping by 68%, that means I'm retaining 32%. So I'm going to take this times 0.32. And when I do that, I get 16. So that means there's 16 milligrams left after day 1. Okay, after day 2, I can take that 16 times 0.32, and I get 5.12. Okay, so to come up with a formula, in this case after D days, I can say that my concentration, I'll just say F of D, is going to be my initial amount, 50, times the amount that I have left, so I'm going to have 32% left each day, to the D. Okay? So this would be an example of an exponential decay because I'm getting smaller each time. Alright, you can also refer to page 108 for a list of properties of exponential functions. Basically, we've talked about exponent properties and things like that. There's just certain properties about exponential functions that you might want to take note of, especially things like asymptotes and certain points that exponential functions always go through, what your a value really means, where it is on your graph, things like that. Okay, and then we've got the homework down here. So that's everything for section 4.